Okay, new microphone, brand new mic. I bought this this weekend, so it picks up voice very well. You can say hi to Marlene and Devin as well.
Hi, Mar. What up, Devon?
Whoa! Wow, Devin and Marlene, I was not prepared for that. That was Chrissy Munson. You can't tell. Marmar, and Chad. Oh, Devin, I'm sorry, I don't get the joke. Okay, all right. Here we go. Please take out your calculator. Type in sine of 1 over x. This is where we left off. We need to investigate this a little bit further. You got to understand it fully, which you do not yet. You do not yet fully understand this. Okay. You're right. The limit does not exist. We need to investigate why. Boys and girls, girls and boys, please. Remember what you have to say is not important at all. So we say sine of 1 over x. And I want to investigate this a little bit more intelligently. Okay. Let's start by adjusting our window. And let's adjust our window. X minimum, let's go to -6. Max to +6. And as far as our y values are concerned, let's go -1 and +1. Let's make sure that you're there, and then we'll move on. Everybody good to go? Okay, give me another second. So I'm changing my window so I can get a better view of this thing, and we can really understand exactly what's going on. Because this is really important for your understanding. We all agreed on Friday that the limit of this function did not exist. Okay, let's graph it. All right. Let's look at one value right now. As I approach, as my x value approaches, let's say, infinity. Let's say I was to go way out here. Can you tell where is this function going towards? What? Its x value is going towards infinity. What is its y value going towards? It would be going towards 0. Let's see if we can make some sense out of that, though. Okay? For example, if I said the limit as x goes to infinity of sine of 1 over x, what you would be doing is you would be plugging in values that are really, 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 really big, right? For example, you would say the sine of 1 over a million. So 1 millionth. That number is very close to what? 0. And what is the sine of 0? 0. Good, all you trig students. Sine of 0 is 0. So as you can see from our graph, that as you head towards infinity or negative infinity, the graph heads towards 0. Why? Because when you plug in big numbers, 1 over a big number becomes 0. But watch what happens when we do this. Take out your calculator, and let's now go to second table set. In your table set, make sure that your independent is set on ask. Make sure that your dependent is set on auto. Everybody good to go? Second table. Now I have a bunch of values out there. Let's try doing exactly what I just did to confirm it. Let's plug in 10. Plug in 100. Plug in 1,000. Way to clear yours. Is that everybody's? Are some people getting these values? and you change your window to a y max and y minimum negative 1 positive 1. Okay, are you working in radians instead of degrees? Mode. You should be in radians. Okay, so if we look back at our table, you can tell that as we plug in large numbers that the value of this function is becoming very, very close to 0. But now let's try approaching 0. This function is supposed to be approaching 0. Let's plug in different numbers. Let's plug in 0.9. And we get 0.89. Let's plug in 0.8. Now it jumps up to 0.94. Let's plug in 0.7. Now we get 0.98. Plug in 0.6. 0.99. Plug in 0.5. 0.90. 0.4. 0.59. If I plug in 0.3, now I get a negative 0.19. What's happening to this? Okay, Ella's right, it's going up and down, but why? Does not have an asymptote inside here. It does not. If we look at the graph, there's actually no asymptote inside here. It's pronounced either way. Here's what's happening. We're now heading towards 0. Okay? We're looking as the limit as x approaches 0. And I'm saying if we plug in 0.9, what is 1 over 0.9? 9. And if we do sine of 1 over 0.8, what is 1 over 0.8? 8. You're starting to get actual integer values, right? You tell me, what does sine do for numbers from 1 to infinity? If we were to look at the graph of sine, what does it do? It oscillates back and forth. And so because when you plug in numbers between 0 and 1, you end up with these kind of numbers, and it oscillates between those numbers 1 and negative 1. That's what's happening. So that's what my point is this. In calculus, and as we examine limits, it's not always that we could just simply plug numbers in. It's not always that we could just look at a graph. Sometimes you have to look at the graph, look at the numbers you're plugging in, look at the table, and understand the nature of the function to begin with. So there's really 4 pieces sometimes to really being able to understand it. There's not always one simple way. And so as we examine that, we'll end with this. Before we move on to the next problem, we talked about zooming in on this before, and when we did, you can tell that you get this crazy looking piece. In fact, this is why we call, anybody know what we call this function? It has a special name, the barcode function. Do you see why it's called the barcode function? Yep, barcode function. So we move on. All right, flip your notes over. What's that? We'll see how well behaved you guys are. Yep. So Derek's question, what do we do here? Yes, you can just draw something that looks like this. The idea it's a barcode function. The limit does not exist. And you're going to see that come up in your homework where it oscillates very quickly up and down. This is the barcode function. It's very interesting to examine. That's why we do it. And just to refresh our memories from what we did on Friday, remember that this function you could not actually evaluate at +3. However, it still did have a limit. It doesn't have to be within the domain. You don't actually have to be able to find a value there in order for the limit to exist. So let's now talk about one-sided limits. Left-hand limit. This is the notation. Question. A limit is as an x value approaches a specific number, the output approaches a specific number. Ask it one more time, Kelly. So the question again is, how might we define a limit? Let's see if this works. If we have the function f of x is equal to x squared, and we want to know the limit of f of x as x approaches 0. What does that graph look like? It's a parabola, and it's centered at 0, 0. So the question is, if I have an x value here, an x value over here, the x values over here are negative, the x values over here are positive. As I run these x values closer and closer, the output, so the green, approaches what number? Yeah. So as the red approaches this 0 mark, you can see that the outputs also approach an output value of 0. As x approaches 1, then we would be running towards this spot right here. If x was approaching 1, we'd be looking for that spot right there. Question, Derek. No, we just have 1. This is it would be 1 squared would be 1. Because you were dividing by x minus 3. Okay, let's try one-sided limits. If you don't understand after that, we'll talk a little bit more. Left-handed limit, what does that mean in plain terms? Approach from the left or negative. So as we're talking about approaching, we're really looking at both sides. Right now we're going to talk about one-sided limits. A right-handed limit has this notation. The limit as x approaches a from the positive of f of x. And that really means we approach from the right. Or the positive. That's why there's a positive. The most confusing piece, I think, to people about this is as they see notation like this, the limit as x approaches 2 from the negative, they think that this means negative 2. No. This means I approach 2 from the left-hand side. If it was a negative 2, you'd see a negative in front. Let's look at some examples. It says let f of x be the graph to the right. Use the graph of f of x to evaluate the following limits. True or false? I could draw the graph of f of x without picking up my pencil. False. True or false? F of x has an output value for every value between negative 6 and positive 5. Looks like it's good all the way up until we get to positive 4, correct? There's a hole there. Okay? So, here's what we look at. The limit as x approaches negative 4 from the negative. So I find my value negative 4, which is right here, and I'm going to approach it from the negative or the left-hand side. So as I approach it from the left-hand side, what's the output value approaching? 3. It is approaching 3. The output value, so the height value, the y value, approaches 3. If I actually plug in negative 4, do I get 3? Yeah, you do. It doesn't always have to be that case, but in fact, your value is 3. Let's approach negative 4 from the positive. If I approach it from the positive, then I'm coming from the right. So I'm going to approach negative 4. What's the output approaching? Negative 2. Crucial that you understand this question. If I plug in negative 4, do I get negative 2? No, if you plug in -4, you get 3. So it's okay if the limit is different than the actual function value at that spot. It's what it's getting close to. Okay? It's what it's getting close to. -1 from the negative. What do you think? Very good. As you approach -1 from the negative, you approach an output value of 4. What about -1 from the positive? Same spot. What do you know? You notice here that there is no break within the function, that it's continuous all the way through, and so those happen to be the same. How about as you approach positive 4? Well, I don't have it specified there. Let's skip that one. Let's just go to 2. Okay? Let's go the limit as x approaches 2 from the negative. If you approach 2 from the negative, you're right, you get -1. How about as you approach 2 from the positive? Approach positive 5. You could cross off E, okay? But now I'm going to ask a very interesting question, okay? You said that the limit as x approaches 2 from the negative is -1. Would you all agree? You said that the limit as x approaches 2 from the positive is positive 5. Would you all agree? What if I take off the positive and the negative? What is the limit as x approaches 2, period? Does not exist. Because of this, okay? Formal definition of a limit. Limit as x approaches f of x is equal to L if and only if the limit as x approaches a from the negative of f of x is the same as the limit as x approaches a from the positive of f of x is equal to L. In other words, the right-hand limit and the left-hand limit have to be the same. If the left-hand limit and the right-hand limit are the same, then we have a limit that exists. Very good. So, yep, so we'll go back to it. For what? For E? We're going to do E here in a second. Okay, so as you look back up, as x approaches -4, I'm not asking right or left hand, does the limit exist as x approaches -4? No. Does the limit exist as x approaches -1? Yes. Does the limit exist as x approaches positive 2? No. Does the limit exist as x approaches 4? Yes. What is the limit as x approaches 4? 2. Hold on. If I plug in 4 to that function, do I get a value of 2? No. So, as you notice, down here at the bottom of the notes, I put something important. Note that f of a, when you plug in that value, it does not have to be the same. For example, let's just change this function slightly. Instead of having, we'll have an open circle there, but we'll actually close it there. As you plug in 4, you get a value of 6. That's okay. The limit is still 2 because the left hand is 2 and the right hand is 2, so the limit is 2. Doesn't have to be the same as what the function evaluated is. In fact, the function doesn't even have to be evaluated at that single spot. That's the definition of a limit. Left has to be the same as the right. Okay? Do you have your books? Let's practice a couple problems right now. Please take out your books. Okay, so here's what I want you to do. As opposed to going on to the next part, which is tables, we're going to do that in 7 minutes. But I'm giving you 7 minutes to look at these 3 problems, which are identical to what we just did in class. Okay? So where we looked at approaching the left and approaching the right, same process. Start with problems 4, 6, and 9. In 7 minutes, I'm moving on to the next portion of the notes. Okay, you guys have been asked to identify limits by looking at the graph. What if we were asked to identify limits by looking at a table? Well, you guys have we could actually form a table by hand, or you could use your graphing calculator. So in this piece, if we go into y equals, it says it wants to evaluate the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, Ben Jones, a good friend of mine, I don't know if you guys know him, some think he's fairly intelligent. I think the jury's still out. We'll see. He says that he has a nice way of solving this. Takes intelligence to know intelligence. All right, so I'm left out on that one. So as you look at this one, Ben had a nice way of kind of solving this. But let's not solve it algebraically, because we're going to do that later on this week anyway. It says use a table. So what I want to do is I want to know if I plug in 2 to this function, do I actually get a value? No, 2 is not part of the domain. If you plug in 2, you don't get something because you would have 0 in the denominator. So let's go to our table here. Let's type into our calculator x squared minus 4 divided by x minus 2. Now, we want to look at the table values. So I go to table, and we want to approach 2. So you tell me, what do I have to check? I want to know the limit, so I got to check which side? I got to check the left, and I have to check the right. So if I want to check the left, what kind of value should you plug in? 1.9. And after I plug in 1.9, I should plug in? No, 1.99. And after I plug in 1.99, I should plug in 1.999. So I'm plugging in numbers that are extremely close to 2, but from the left-hand side. What does it appear like it's approaching? 4. But it's not enough to just check one side of it. I also have to check the... So what should I plug in? 2.1. And after you plug in 2.1, you should plug in 2.01. And after 2.01, you plug in. So this exercise is to make sure that you can confirm by tables exactly what the limit is approaching. What's the limit approaching? 4. Now, just to confirm you guys, okay, if I wanted to know what f of 2 was, what would you say? Can I actually plug 2 into this function? We said you can't. But the limit does exist. So even though you can't plug it in and get a value, you can approach it and still get a value. Let's look at the next one. Again, we want to be working in radians. I think everybody's calculator should be there. We go to y equals, and we got sine of x divided by x. And we want to approach 0. So I go to my table. What kind of numbers should I plug in? Let's approach from the left-hand side. So let's go negative 0.1. After negative 0.1, negative 0.01. Negative 0.001. What does it look like it's approaching? 1. But I check from the left. Is that enough? No, I must check from the right. What value should I plug in? You can see that for sure this limit is approaching positive 1. Any questions on using a table? Could you use a table? Okay, that will be a portion of your problems. Let's move on to the next set. Oh boy. Okay, in our calculator, let's examine these limits. These are a little bit different. X approaches 0 of 1 over x to the 4th. Let's actually type in our calculators 1 divided by x to the 4th. Now, this function is actually not able to be evaluated for one value. Do you know what number you can't plug in? 0, which is what you're approaching. So, as we look at this graph, everybody got that plugged in? Now, let's zoom 6. Let's all zoom in the same standard window. Zoom 6. Ben Jones likes this. Unfortunately, he's going to see some of his theory fall apart as we look at this, and that's okay. All right. Would you agree that that is that's the graph? Well, a representation of the graph. So as you approach 0 from the left-hand side, what does the graph approach? Positive infinity. So as you approach from this direction, you approach positive infinity. As you approach from this direction, again, I'm approaching 0. I'm approaching this spot. What does the graph approach? Infinity. Are those the same? So the limit is defined to approach infinity. This problem, which one? What are you talking about? Right here? No, it's approaching 0. And this is approaching 0 as well. It's okay. It's okay, Ben. 2x plus 3, parentheses, divided by x minus 1. Whoop. Make sure we get our parentheses in there. X minus 1. Okay. We graph. Oh boy. Now we have examples, as we've said before, of asymptotes. This one, I have a TI-83, you have an 84. Mine's not as smart as yours. So, would you guys agree that that's a representation of the graph? Ina says no. Oh, okay. So it dips down here. It's okay. It's okay. It's gonna be okay. All right. So as we approach x, as we approach 1 from the negative, tell me, what is the output approach? The output approach is negative infinity. As we approach 1 from the positive, what is the output approach? What's that? Yes. And because you have two limits that are as polar opposite as they could possibly be, what do we then say about the limit? Does not exist. Can we say we put a crushing blow to the Ben Jones theory that a vertical line has a slope of plus or minus infinity? It has a slope that is undefined. As you can see here, the limit does not exist. No. No. What's that? That's your example. I think that's all we have time for. There you go. There's your assignment.